minus log transmittance is the absorbance. I know several GSIs asked this sort of question on the quiz last week, was, if you had a transmittance of 10%, what is the absorbance? So we can do that. So if transmittance is 10%, that's the same as 1 over 10. What's a log of 1 over 10? Minus 1. Since this is log minus transmittance, the absorbance then would be minus the minus 1, so the absorbance would have been 1 OD unit. If it was 1%, that's 1 over 100. It's the same as minus 2, so the OD would be 2 OD units. Okay? Minus log of transmittance is the same as the absorbance. This one makes sense. The more transmittance, the less absorbance, right? So less transmittance, the more absorbance. Okay? All right, so we won't worry about the identification. You've had a lot of this already about the R groups and that. I want to go over it just a little bit again. Remember, with amino acid, we have the amino group, the carboxylic acid group, and the R group. It is the R group that varies between the amino acids. You should, if given a structure for the amino acid, be able to know if it's hydrophobic or hydrophilic, okay? So basically, if you look at something like this, these consist mostly of carbons and hydrogens. So these have pretty much the same electronegativity. So they would grab electrons about the same. So they would be polar and nonpolar. Nonpolar. When you have things that don't grab electrons equally, that's when you establish polarity. So we have some amino acids that act as the R groups are acidic, aspartate and glutamate. So here's a question. Remember, these things can go back and forth. Lose the proton, accept a proton. So we can draw that. Right? That equation is this. So here's the R group. This would be for aspartate. Here's it protonated. Here it is unprotonated. Here's the pK of this group. I made this pK up. Okay, I made it up. It's 5.3. What that pKa means is that pH 5.3. If that solution, that amino acid in a solution of pH 5.3, 50% of those molecules exist as the unprotonated form, and 50% exist as that form. That's what pK is defined as. It is the pH at which you get 50% of each form. So what form would predominate if I took that solution at pH 5.3 and I started to titrate it with some acid? And I titrate it to a pH of 5. Which group would be more predominant in terms of percentage? Would it be group A or B? So think about that. Ask your neighbor. Discuss it. Okay, I didn't bring my clicker receiver, but we can still do this by show of hands. Those who think A would be the most common form, raise your hand. Fair number. Those who think B? A few brave souls. It should be A as an apple. So let's just figure out why it would be that way. So pH 5.3, we want to titrate it to 5. Are we going to add protons or remove protons? Add protons. So Le Chatelier principle would say which way do you drive the reaction? To the left. Because if you increase this, you drive to the left, so that's why that is the more predominant form. Okay? How many of you actually wrote out the Henderson-Hasselbalch equation and tried to solve that? You could. It would work. All right? But that's a fast way. Does that make sense? I guarantee I will ask you to do this on the lab exam. I will give you some R groups, some pKa's, and ask you which forms are predominant. And that's important because if we had two R groups at the active site, and if it was a plus, let's say it's a minus-minus charge, would that be a favorable interaction? No. So in fact, they would repel one another. But as you change the pH of that local environment, you may get one to be minus and neutral. Would that therefore be an unfavorable reaction? No. It'd be relatively neutral. If it was a minus and a plus charge, it would stabilize that active shape, that active site, and maybe increase catalysis. So you definitely need to be able to know that. Usually what I do is I give you several R groups, then I say which pH would be the range at which you would find the favorable interactions. So you look for minus and plus, okay? Again, application, you'll be able to do it. Yes? Yes? So the question is equilibrium. So equilibrium is when the forward and reverse reactions are the same, correct? That's what equilibrium is. Has nothing to do with ratios, but it's the equilibrium, right? Forward reverse. But in this case, knowing that pKa, that is the ratio is 1 to 1. So by knowing pKa, you know at exactly pH 5.3, there's exactly 50% like that, 50% like that. So when you increase the concentration of one side, you drive the reaction to the other side, okay? Now, so you got to think about the fact that this pKa definition, okay? All right. So let's just move on. Realize that in the cell, you make a protein through ribosomes, and what you do is you link amino acids together, a dehydration reaction to form that peptide bond. And this is actually very misleading. So if you notice, does nitrogen like to have electrons? Yeah. How about oxygen? Yeah. So in fact, there's resonance between here. So this is actually a planar bond. So this actually, the peptide bond is always labeled here, but it's effectively the electron resonance between these two bonds. It's always labeled here. So in fact, this is a planar bond. And that dictates a lot about how these amino acids can link together and then fold to form your various secondary structures. So remember, primary structure is the actual linear sequence, and there is a polarity. That is, there's an N terminus and a carboxyl terminus. Polarity is a very important thing to wrap your head around. Polarity of DNA, 5' to 3'. Polarity of amino acids, amine group, carboxyl N. Polarity of proteins, amine terminus, carboxyl terminus. So there is a polarity here, and what you'll see later is that when you synthesize the protein within the cell, it's always from an N terminus to a carboxyl terminus direction, and that's reading the RNA in a 5' to 3' direction. Okay? So you get a lot more on that. So the various levels, primary is strictly that just linear sequence. We usually, by convention, start with the N terminus and proceed to the carboxyl terminus, but not always, but usually. We have different forms of secondary structure. Now, this is the alpha helix. Remember, when we have a backbone like this, if I read the backbone, it would be NCC, 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 NCC. So when I go along that backbone, it's NCC, NCC, and notice there's going to be positions where there's a carbonyl group, and over here, there's a position where there's an NH group. What's the partial charge in this oxygen? Minus or plus? Minus. And what would be the partial charge in this hydrogen? Plus. So in fact, the reason why these helixes in that form is because there's a carbonyl group sticking up, and there's an NH group sticking down, and you have that partial negative and partial positive charge stabilizing it. The best analogy I can think of is imagine a slinky. You pull it up, so it's apart, and you can follow the helix of the slinky. If you had toothpicks coming off of this at various angles, those would be the R groups extending out from that helix. But along the helix, if you put toothpicks to glue it together, keep it space, those would be the hydrogen bonds along that backbone. So if I could just have the Elmo here. Can you see that? Okay, so let me zoom. So this is just showing you, this is that helix, there are hydrogen bonds along the backbone stabilizing this, but also notice it's flexible, and that's true for the proteins as well. Various things can stabilize it, so that might be that shape because there's a disulfide bond there. Bond. It's a very strong bond. So this disulfide bond, kcals, about 100 kcals. What's a hydrogen bond, kcal about? About 1 to 3. So they're not real strong, but there's so many of them, it's the hydrogen bonds that stabilize this sort of structure. Okay? So just keep that in mind when you think about the secondary structures. It's along that backbone, and again, it involves the carbonyl and the amine group. And it doesn't show it here, but beta-pleated sheets, same sort of thing with beta-pleated sheets. I'll just show that here. Along the backbone, positions where we have the carbonyl group, and then positions where we have that amine group, and there's the partial negative here, the partial positive there, and there's the hydrogen bond. So it's a summation of all those that stabilize the secondary structure like that, okay? And it typically alpha helix and beta-pleated sheets. Secondary structures involving the backbone. Tertiary structures involve the R groups interacting, whether hydrophobic or hydrophilic or partial positive, partial minus. Question. So the secondary structure depends in part on the primary structure, okay? Because certain R groups will prevent the formations of the helix. For example, a proline in there introduces the kink, so it minimizes the formation of alpha helixes. So various groups will lend themselves towards an alpha helix or towards a beta-pleated sheet, okay? So in fact, the holy grail of sort of protein folding and stuff is we hope that when we get enough X-ray crystallography structures of proteins, we can come up with some folding rules and some predictions, okay? In fact, I have this annual contest where what happens is various scientists get together, they have an unknown structure, they're given a primary sequence, and the various groups of scientists try to predict what the structure will be without actually knowing it because it's been kept secret, and the group that's the closest wins the prize, okay? So the bottom line is we're hoping to get better and better with that because getting the sequence, the primary sequence, is super easy. We can get the sequence of genes and therefore the sequence of the protein very quickly. We could take an unknown organism, we could grab one of the bacteria from the lab that we haven't defined, and we could sequence the entire genome in probably a week. We could predict the protein products, not with 100% accuracy, but we could predict protein products of almost every gene there. We could then try to predict the structure, but we wouldn't be real good. But we'll do more about that in bioinformatics, okay? Because you'll see various tools to do just that, okay? So there's a lot you can do with the sequence, and it's super easy, super quick, and pretty cheap. Soon, we can sequence the entire genome of a human for $1,000. It used to be several million, and do it in a week. Question. So the question is, with a beta-pleated sheet, is it intra-polypeptide? That is it within just one polypeptide, or can it be between different polypeptides? Is that correct? Was that the question? It could be either, okay? If it's between polypeptides, that would be an example of quaternary structure, because there's more than one subunit, but it would be beta-pleated sheets that stabilize that, okay? So all proteins have to have a primary structure, and all proteins have to have a tertiary structure, but they needn't necessarily have secondary or quaternary. Some actually, they just do what's called globular folding. There's no really secondary domains. Anyway, this is just trying to illustrate this. This is what I did on the board. Notice those hydrogen bonds that stabilize it, okay? And here are the beta-pleated sheets. Notice the hydrogen bonds that stabilize it, okay? And sometimes they talk about them being parallel or antiparallel. Again, it's referring to the polarity of the N-terminus and carboxyl terminus. Now, this is hemoglobin. 4 subunits. This is showing you a ribbon molecule. This is showing space filling. These tend to be a little bit more accurate. If you have ChemView and various things like that, you can go on to various websites, pull up these molecules. You can rotate them. You can sometimes get coordinates for them, play around with them. In fact, a lot of people who do X-ray crystallography use it now for gaming theory. So they basically have gamers go on board and try to figure out the structures, and it's become a pretty interesting area for gamers to get on board. So remember the reaction profile here. We go from substrates to products. The delta G is this difference between the substrates and products, okay? And this is the energy of activation. The enzyme lowers the energy of activation, so the reaction should proceed faster for a given situation. Now, does it change the equilibrium? No. Does it change the delta G? No, okay? So there's one graph that's always been left out of biology books, which is unfortunate. So here shows the reaction profile. All the books have that. Here shows you the Boltzmann energy distribution. This is temperature 1, temperature 2. When we heat up, so like in OChem, when you heat a beaker of water or whatever happens to be chemicals, you drive the reaction such that you change the distribution. Just like when you put a pan of water in the oven or in the stove in that, you change the temperature. So you shift it to the right, you spread out the peak and sort of spread out the distribution. If you need this much energy of activation to undergo catalysis, so those molecules have sufficient kinetic energy to overcome that energy of activation, that population of molecules are those that can undergo catalysis. That's why when you heat up the solution, you increase the rate. More molecules have sufficient energy. Is that clear? Because what you're doing is you're changing the distribution profile. Cells can't do that typically. So what cells do is because they don't change the reaction profile, but they change the energy of activation, so they effectively move this point to the left. So we now have this increased number of molecules that have sufficient energy. That's why the reaction rate goes faster. You haven't changed the distribution profile, you just changed the energy of activation required. It's a lower energy of activation, therefore more molecules. Is that kind of clear? Any questions about that? So the enzymes aren't changing the profile at all, they just change the number of molecules that have sufficient energy because they lower the transition state. And how do they do that? How do they lower the energy of activation? Various ways. So if we just take this reaction, these two molecules, let's say it has a rate of 1, whatever happens to be a rate of 1. If we take and change these two substrates so that they're now linked together, so now the two substrates are in close proximity. So an enzyme can pull the substrates together and put them in close proximity. This, again, no enzyme involved, this is just illustrating what the enzymes can do. In this case, the reaction rate is increased 100,000-fold. No enzyme, it's just illustrating how proximity can change the rate. In this case, what we've done is we have these in a specific orientation to drive the reaction. So we have both proximity and orientation, and we increase that another 1,000-fold relative to that. So overall, we've increased this 100,000-fold. Okay? Sorry. Yeah, so that's a big fold, right? Increase. So that's what enzymes are doing. They're orientating the substrate in the right orientation and proximity. They strain the bonds, things like that. Okay, for the lab, so that's just the general background. Now for the lab itself, it's relatively straightforward. A few key points. We have amylose as the substrate. That's also called starch sometimes, amylose. The enzyme is amylase, ASE for the enzyme. The product that we're looking for is maltose. Now, we will not measure maltose directly. We do not have that ability. We will measure it indirectly. The way we measure it indirectly is we'll add a chemical called DNS. And DNS, when heated at greater than 95 degrees C, it will react with the maltose because it's a reducing unit and produce a brown color. We measure in the spec. More brown color, more maltose. Less brown color, less maltose, less activity. So that's basically what we'll be doing. Now, amylase is the enzyme. It converts amylose to maltose. There's this term called isozymes or isoenzymes. That means they do the same reaction. That is, same substrate to same product. But they have different primary structure. Now, you may have heard of salivary amylase in your mouth. You also have pancreatic amylase. They have different primary structures. They have different amino acid sequences. But at the active site, they're relatively similar because they have to catalyze the same reaction. So those are called isoenzymes or isozymes. Same reaction with different primary structures. They have to have some conservation at the active site because they're doing the same reaction. Okay? So different genes. The pancreatic amylase is encoded by an amylase gene. The salivary amylase is encoded by an amylase gene. They're different genes. Salivary amylase gene is active in your salivary glands. The pancreatic amylase gene is active in your pancreas. Okay? So you're not turning on the pancreatic form of the gene in your mouth, although you have it there, because all your cells have the same genes except for a few. This shows you a sort of a space fill model of this. This is where the starch would bind. So this is starch. This is only 5 long. Starch varies in length. This is 5 glucose units long, alpha 1,4 linkages. There's some molecules that help it in terms of prosthetic groups. There's a calcium, chloride, iron here. There's 3 amino acids here. They're acidic. They help to catalyze the breakage here. So can't see this real well, but that's pink there. Here's maltose, the disaccharide that will be cleaved off. Here's the remaining 3. So in fact, for the amylase, the substrate when amylose comes in could be really big, and it will cleave it off typically as the maltose, okay? I would never ask you how many acidic amino acids are involved at the active site. It's not a question I would ask. Just realize that they're doing something at the active site. All right, so this illustrates this here. This shows a long polymer, alpha 1,4 linkages. So amylose is here. Amylopectin is similar, except it has a bunch of additional branches. We're working with amylose. Here shows this only as a 4 of them, but in fact it can be very long. It can be 5,000 long, 10,000, 100,000 long, okay? So anyway, so it's pretty big here, okay? So just showing you 4. Linked by an alpha 1,4 linkage. It has a polarity, okay? So this end is different than that end. Let's just look at glucose. I know Dr. Down has done this. I really want to try to stress this. Here's just showing you the linear form of glucose. It can form a ring form. So the number 1 carbon, 2, 3, 4, 5, 6, forms the ring structure. There's that oxygen there. This OH can either be up or down. If it's down relative to the plane of the sugar, it's the alpha form. And if it's up, it's the beta form. So the linkage here, these are all alpha 1,4. Starch, potato starch, corn starch, those are all alpha 1,4. Wood, cellulose, those are beta 1,4s. Very different structure, although it seems like they should be so similar. That alpha beta is a big difference. I do want to point out that these are free to go back and forth, back and forth, back and forth, okay? So if I could have, so here's just again showing this back and forth. So this is the beta because it's above, there's the alpha. All right, now if I could get some volunteers, here this row, come up here please. They're not really volunteers. It's a bad choice of words. I need some student demos here, okay? Those are actually glucose molecules, each one. So, come on over here. Glucose. Put your hand like this. I mean, just this one, okay? Just that one. Okay, go ahead. Okay, link. So, glucose, I'm forming this polymer. There's the alpha 1,4 linkage on the hips. Link. Hips. Then we're going to have to do some stepping. No. Okay? Like this. Like this. Form it like that. Okay. Those are the alpha 1,4 linkages. So there's a polarity here, okay? So notice, he's free to do this with his arm. He's free to go from a ring to a linear form, right? And he doesn't affect any other bonds. There's polarity here. But if he does that, he's broken this bond. So only the terminal glucose in this polymer is free to go from linear to ring. Only the terminal. That's going to be a key aspect, okay? So when I have a polymer that's 1,000 long, I have one potential linear to ring conversion at this end, but nowhere else. So I have one reducing unit. If I take and have a disaccharide, so amylase is acted, I can now still have the one reducing unit. But this still has a reducing unit because I just created that. But now if I get the 2 maltose, 2 reducing units, right? So as I cleave this, my number of reducing units keep increasing, right? Thank you. That's good enough. It seems to be a subtle point that's lost every semester, so I try to stress it. So when we have a polymer like this, there is a polarity. And only one end, this terminal over here, is free to go from ring to linear. So only one end has a reducing unit. No matter how long that polymer is, there's only one reducing unit. Okay? When we cleave this, in this case 4, into 2 maltose units, we now have this, which can go to the linear, which will then have that aldehyde, which can then react with the DNS. So as a result, we will, as we cleave this polymer into the maltose, we will be increasing the number of reducing units. But we always have to take into account the background from the original starting molecule. So we need to have blanks in this experiment. We're going to be measuring the OD change. So we have to have blanks that take into account the background of the starch, because each starch molecule has one reducing unit. Question? So if you look at this, there's a 1, 4 here. So this end is 4, this end is 1. So there's a polarity there. So here, this is a 4, that's a 1. So along this entire chain, there's that polarity, okay? Does that make sense? The number 1 carbon is different than number 4, right? And so I can say this is different polarity because this is the number 1 end here, that's the number 4 end there. So there's a polarity here. So only at the number 1 end can we do that, okay? I'm sorry? Okay, so the question is which end is more electronegative? I don't actually know, okay? And I don't know if it makes a difference, but I just don't know, okay? The bottom line is this is the only one that can go ring to linear, because this is the only one, if you did it here, you'd have to break that bond. Remember how over here, we had to break the bond to get that to go ring to linear? So only the terminal one can do that, okay? All right, so let's just do the experimental setup. This is always true, okay? So you can write this down. There's always half a mil of enzyme. So no matter what reaction we do, it's a half mil of enzyme, or half a mil of diluted saliva, because in some cases we'll be using diluted saliva. It's always 1 mil of substrate. It's always